In the previous video, we saw that current flowing was equal to QNUA, where A is the cross-sectional area of the conductor, U is the drift velocity, N is the number of conduction charges per unit volume, and Q is the charge per conduction charge. Let's divide both sides of this equation by the cross-sectional area of our conductor. The unit of current is amps. The unit of area is meters squared. So the units of this I over A is amps per meter squared. That is what we're going to call our current density and give it the symbol J. Current density is something that occurs at a point in space. And the current density is flowing in the same direction as the drift velocity of the particles. So we treat current density as a vector. Let's look at this term Q times N. So Q is the charge per conduction particle. N is the number of conduction particles per cubic meter. So Q times N is going to have units of coulombs per cubic meter. Q times N is the amount of charge per unit volume at a point in space. This is something we've encountered before. That is just the volume charge density. So we can rewrite our equation for the charge density as J is equal to the charge density times the drift velocity with which that charge is moving. The volume charge density of the conduction charges will be a material property. So for a substance like copper, it will have a fixed value for this rho sub v, the charge density of the conduction electrons in copper. Let's focus a little on this drift velocity. The drift velocity is proportional to the electric field intensity. So you double the electric field intensity, you'll double the drift velocity of the conduction charges. You have all made measurements that verify this relationship. When you've measured the IV characteristic for a resistor, this linear relationship between the voltage and the current is a consequence of the fact that the drift velocity is proportional to the electric field intensity. We're going to use mu sub E as the proportionality constant between the drift velocity and the electric field intensity. So for an electron, the drift velocity is equal to minus mu sub E times the electric field intensity. The minus sign coming about because the velocity is in the opposite direction of the electric field, and we want to treat this proportionality constant mu sub E as a positive quantity. This proportionality constant mu sub E is referred to as the electron mobility. It is the ease with which electrons drift in a material. So let's go back to our equation for our current density here. So for our charge density, if we're dealing with electrons in a metal, the charge density will be minus E times N, where E is the magnitude of the charge on an electron, 1.6 times 10 to the minus 19th coulombs. And for the velocity, we will substitute in minus the electron mobility times the electric field intensity. So our current density is going to be En mu sub E times the electric field intensity. For a given material, this quantity is a constant. The magnitude of the charge on an electron, the density of the conduction electrons, and the mobility of the electrons in the material. The product of these three terms we're going to call sigma. So the current density is equal to sigma times the electric field intensity, and this sigma is called the conductivity of the material. This equation is referred to as the point form of Ohm's law. So let's determine the units of conductivity. Conductivity is a current density over an electric field intensity. So we have an amps per meter squared for units of current density and volts per meter for units of electric field intensity, which is an amp over a voltmeter. A volt over an amp is an ohm, and 1 over an ohm is a Siemens. So the units of conductivity is Siemens per meter. And 1 over the conductivity is what we call the resistivity. The symbol for resistivity is rho sub C. So we see the units of resistivity is going to be ohm meters.